Chapter 9, Chemical Bonding, the Lewis Model. So first let's talk about the type of chemical bonds there are. We have ionic bonding, covalent, and metallic. Now, ionic and covalent have already been talked about. An ionic bond happens when you have a metal plus a nonmetal. And what happens is we know that metals tend to lose electrons, nonmetals tend to gain, so in order for an ionic bond to form, they transfer electrons. Now, covalent bonding. Covalent bonding occurs between nonmetal and nonmetal. And since both nonmetals tend to gain electrons, they don't lose either of them, so they share their electrons. Now, what about metallic bonding? So metallic bonding is between metals and metals. And what happens here is that each metal donates its electrons to create a sea of electrons. So we know that sodium solid loses an electron to become a sodium ion. Now, this electron is then in a sea of electrons as more of these sodiums come together. So let's talk about how we represent these different structures. Lewis symbols. Now, a Lewis symbol is a way for us to see what we have, how many electrons we have around a specific element. So really simple. If I were to draw out my Lewis symbol for hydrogen, I would write my element symbol, and then I would say my valence electrons. I know hydrogen only has one, so I would have 1 dot. Now, what about something a little bit with more electrons? Let's do oxygen. Now, from the periodic table, we know that oxygen is in group 6 and has 6 valence electrons. So if I wanted to show my Lewis symbol, I would write my element symbol just like I did here, and then draw my valence electrons around it. Now, that doesn't mean that I go 1, 2, 3, 4, 5, 6. That would be wrong. The way that we look at drawing a Lewis symbol is that it's basically like an invisible square around the element, where each line is an orbital. We know that each orbital can only have 2 electrons. So my Lewis symbol would be 1, 2, 3, 4, 5, 6. Now, I went in an order of going clockwise. It doesn't matter if you go counterclockwise at all. What is really important is the fact that we've learned from all of our rules from chapter 8 with the alpha principle, slowly building up the electrons and energies levels, the Pauli exclusion principle that an electron has to have opposite spins if both of them are in one orbital, and then the Hund's rule that you fill 1 electron in each orbital first before you pair them. So we have to place 1 on each side since each side of the square is an orbital and then pair them around. Again, it doesn't matter if you were to go clockwise to do this or counterclockwise as long as you're going in an order of 1 in each before you pair. Now, when we have a stable molecule, we always want 8 electrons. Know how right here my hydrogen only has this 1 electron by itself, and my oxygen has these 2. Now, this one singular oxygen makes hydrogen extremely reactive. It constantly wants to bond to something else. And oxygen really wants 2 more electrons to become stable, whether that means gaining 2 electrons from a metal or sharing 2 electrons with a nonmetal. If then oxygen would gain 2 more electrons, it would become an ion with a 2- charge since we gave it 2 electrons, and now it has a full octet. So octet means is an atom's ability to stabilize if it gains or loses enough electrons to reach a noble gas configuration. Let's look at what I mean by that specifically. So for oxygen, what is my electron configuration? 1s2, 2s2, 2p4. Now for my oxygen 2-, I have 1s2, 2s2, 2p6. My energy level 2 is my last energy level, and I have 2 plus 6, 8. So now I have my octet, my noble gas configuration, because I could just write the noble gas for this, and I'm completely stable. Now, this applies to all elements except for 2. Hydrogen can't gain 7 because hydrogen and helium, I'll write helium up here next to it as well, with its 2 electrons, only have an s orbital. The hydrogen electron configuration is 1s1, and for helium, it is 1s2. There are no p orbitals there. If we think of an s orbital, it can only occupy 2 electrons. So there's no more room for electrons. Therefore, they can't have an octet. They have something called a duet. So hydrogen and helium are stable when they have 2 electrons and make a duet, where other elements will be satisfied with the octet 8 valence electrons. In a Lewis model, a chemical bond is the sharing or transfer of electrons to attain a stable configuration. So we represent this in ionic and covalent compounds to show how the different metals and nonmetals are coming together to satisfy an octet for every single element in the compound. Let's start with ionic bonding. So if we were to ignore everything else here and just look at potassium and chlorine. Now I know this is my metal and this is my nonmetal. So they cannot make a bond. They have to transfer their electrons. Chlorine has 7 valence electrons, potassium has 1. Now let's take a moment before we continue to go back to the electron configuration. My electron configuration for potassium is 1s2, 2s2, 2p6, 3s1. And for chlorine would be 1s2, 2s2, 2p5. So I can see that chlorine needs 1 more electron here to satisfy its octet and become a noble gas configuration, stable. The reason that we're always looking for noble gas configuration is because we know that the noble gases have their shells completely filled and are very, very unreactive. This is our goal, because if your element is continually unreactive, then it's going to be left alone by things that are in the air around it. Potassium, if we look, okay, 1s2, 2s2, 2p6, this is all happy and filled. 3s1. Well, this 3s1 is really, really reactive, this electron here. So if I lose my electron, I then also find my noble gas configuration and become more stable. So I know that my potassium will donate my electron to the chlorine. Now, this doesn't mean that I can just write that, because this doesn't show what happened with the electrons. Once potassium loses its electron, it's no longer K. It becomes K+. 1s2, 2s2, 2p6. Since you write the plus, I know that there was an electron lost. Just like chlorine, chlorine becomes chloride. The minus tells you that you have 1s2, 2s2, 2p6, the gaining of the 1 electron. Now you have to indicate that with writing a Lewis symbol for an ionic bond. The way we do that is in brackets here. So now potassium becomes an ion. It doesn't have any electrons around it anymore because we took away the 1 electron from the valence. We indicate that by the plus charge. Chlorine now no longer just has 7, it has 8. So 1, 2, 3, 4, 5, 6, 7, 8. Then I write my minus to make sure that I show you I gained 1 electron here from the potassium. Let's put that all to practice. Take a moment to write the Lewis symbol for the following. Remember that the Lewis symbol will be the element, which is already written for you, and then the valence electrons. After that, take a moment to write the ionic compound for calcium oxide and strontium bromide. So we look at the periodic table and we see, I know that aluminum is in group 3, so I have 3 valence electrons. So I would write aluminum with 3 electrons around it. Again, doesn't matter if you go clockwise or counterclockwise as long as you put 1 on each side before you pair, if you even have to pair. So 1, 2, 3, and you're done. Sodium plus. What does that mean? I know sodium on its own has 1 valence electron because it's in group 1. If I have a plus here, it's gone now. But that means I can't just write Na, I have to write Na in brackets with the plus. This tells somebody that, oh, okay, there's no dot around the sodium for its 1 outer electron because it was lost because of the plus charge. Magnesium. Magnesium has 2 valence electrons. So the 2 plus means that the 2 electrons were given away. So then you also have to put that into brackets with a 2 plus charge on the outside. Now let's look at calcium oxide. Now, calcium has 2 valence electrons. Oxygen has 6. 1, 2, 3, 4, 5, 6. So I know that one of these electrons will go to the oxygen, and so will the other, to give me calcium 2 plus with oxide ion. Next one, strontium bromide. Now there's a 2 here, which means that I have 2 bromides that can make this ionic compound. Strontium is in group 1, and group 2, excuse me, so I have 2 valence electrons, and bromide is in group 7, so I have 7 valence electrons. 1, 2, 3, 4, 5, 6, 7, and then I have another bromine. 1, 2, 3, 4, 5, 6, 7. Now you can see the reason that there's 2 bromides is because strontium has 2 electrons. 1 electron will go to this bromide to fill its octet, and then 1 electron will go to this bromide to fill its octet. Now you necessarily don't have to write both bromides. You can write 1 and put a 2 in front of it. So we would write strontium with the 2 plus since we lost the 2 electrons. Then you can write 2 in front of the brackets for the bromide and write a minus. The reason I'm not writing a 2 minus is because bromine only gets 1 electron, but there's 2 of them. So we still write the charge because there's only a gain of 1 electrons, but the 2 on the outside of the brackets tells us that there's 2 of those exact ions. Woo, this all brings up to lattice energy. Now, what exactly is lattice energy? Before we get too into the nitty-gritty of this, let's look at what I have written here. Now, the first ionization energy of sodium is 496 kilojoules per mole. What does that mean? That means that in order for sodium to become sodium ion, it loses an electron, and that takes 496 kilojoules per mole. The electron affinity for chlorine is only negative 349 kilojoules per mole. So chlorine gas gains an electron to become chlorine ion, and that takes 349 kilojoules per mole, and it's a negative number. Well, we know that sodium ion and chlorine ion can come together to form sodium chloride. However, the amount of energy to form this sodium chloride is negative 411 kilojoules per mole. But if you sum up 496 and 349, you do not get negative 411. Why is that? Where does this energy come from? Now, if you look at my little diagram down here, you can see chlorine is a gas, so there's no liquid, right? This is just a container. The reason that it's contained is because it's closed with a bunch of chlorine ions around it. Another important note is this is Cl2 because chlorine exists diatomically. Then we have our little block here because it's just salt. Sodium exists as a salt. Salts are rigid structures that are highly, highly attracted to one another. Then if I place this salt cube into my gas, they're going to react. But it's not as simple as just the solid and the gas will form immediately sodium chloride. There's a few steps that have to take place. We know that the electrons have to transfer, but in order for electrons to transfer from sodium and chlorine, they have to be ions. That means that I have to make my solid first into my sodium gas, and I have to break up my chlorine diatomic into a singular chlorine, and then also it has to ionize. When these two come together, because they have so much energy, they actually release a huge amount of energy, and that is what the lattice energy is. When you have a bunch of sodium ions and chlorine ions, doesn't matter sodium or chlorine, I should say, cations and anions that come together, they all have so much energy. When they then stick together to form the solid through their electrostatic attractions, they then release a bunch of energy, and that energy is lattice energy. Now let's think about the exact steps it takes. So here's another better picture of this. I'm sorry that it's a little blurry. All the green that you see, that's the chlorine, and all the purple, that's the sodium. So first, you just have the sodium ions and the chlorine ions once we've made them, because remember, sodium is a solid to start with, and chlorine is a diatomic gas, so they are not like this yet. how do we make it like this? I would first have to take my sodium that's a solid and form it into a gas. The reason that I have to do that is because you can only ionize elements in its gaseous form. So that means if I start with a solid, I have to make it a gas. So that would be kind of my first step. Then I can take that sodium gas and ionize it to make it an ion. So now I'm here, great. But I'm not here yet. So I know that my chlorine gas starts as a Cl2. So I have to break this up into chlorine and chlorine. Now I only want one, so a way that you can balance this equation is you put a half here. So now you broke up your chlorine, because remember, this is a Cl bonded to another Cl, and you want to break this bond so you only have one. But again, this is not the ion, this is just one chlorine atom. So then you would say, okay, well, I want to make that chlorine anion. So therefore, with electron affinity, it becomes chlorine anion. Now you have your chlorine anion and your sodium cation. Then what happens is the sodium cation and the chlorine anion come together to form the sodium chloride. And this is how it happens. Now that you have all your cations and your anions, they're going to begin to circulate one another. All the negatives are going to be attracted to the positives, and that's just going to continue, right? So here, this picture is trying to show you that you had them all dispersed in this container, and now they're slowly coming together. Eventually, they are so together that they form this, a crystal, the salt that we see. Now, they all have so much energy. As they come together and form this, they release energy, and that's your lattice energy. So, lattice energy in conclusion, the energy released from this solid crystal by their ions. Now, there's two forms of lattice energy actually, because it could be looked at a absorption of energy or a release. So when you have your sodium, for example, your cation and your anion, and they come together to form a crystal, they're releasing excess lattice energy. The opposite process of that is if you start with your crystal and you want to break up into your ions. In order to break up, you need energy. That needs to be absorbed. So that energy is also lattice energy because you're going the opposite direction to absorb those two ions. Lattice energy in the state that we're talking about, where the ions are coming together to form a crystal, is always exothermic, and it's really hard to measure. So we can't actually go through and find these ions and measure the amount of energy that's released when they come together. The lattice energy is really dependent on the size of the charge, because if you have a higher charge, you have a higher attraction, right? So if I have a +1 and a +1, they're attracted. A +1 and a -1, excuse me. And then if I have a +2 and a -2, they're bigger, so they're attracted even stronger. That gives you a higher lattice energy. Since we're thinking exothermic, higher lattice energy means more negative. They're also inversely dependent on the distance between the charges. What does inversely mean? So if they're directly related to the size, how are they inversely dependent on the distance? So think of if the ions are separating, right? So if the distance increases, the lattice energy will actually decrease because the charge is going further apart from one another. We can calculate this lattice energy by a series of steps. The way that these steps can be pictured is through something called the Born-Haber cycle. Just shows you all the steps it takes to form a certain compound, visualizing the lattice energy. So if we look at what's going on here, this diagram is energy versus your nothing actually, because it's just the steps. So let's see what we got. We got the formation from the sodium and the chlorine. We know that sodium has to ionize. That takes energy. And the chlorine, electron affinity, releases energy. The sodium here has to first become a gas. The chlorine diatomic has to become an individual chlorine. So this is kind of my sublimation right here. Then this is my breaking up the chlorine bond. Then I'm ionizing my sodium. These all take energy, so that's why it's all going up. They're all gaining energy, which is endothermic. Then with the chlorine, because to ionize the chlorine with the electron affinity, that was negative, so that's going down because it's releasing energy. And then when my two ions are coming together, it releases all that lattice energy. The reason you have the opposite process is if I was trying to go from my solid back to my ions, I would absorb the lattice energy. And the sum of all of that gives me my heat of formation. So looking at this in another step-by-step formation, let's look at what we got here. So, doesn't necessarily matter where you start. So you could start with your anion or your cation, but you do have to make sure that you're ready to ionize them. So, we know, if you look at this first, if I cover the rest of this, forming sodium solid with 1 chlorine gas gives us sodium chloride. The heat of formation, the enthalpy, meaning heat of formation, energy of formation, was negative 411 kilojoules per mole. So it released that much energy to put these two ions together. But I know there's steps that are needed to take to make this. So my first step is my sublimation. Sublimation happens when you go from a solid to a gas. So you have your sodium solid to your sodium gas, which takes 108 kilojoules per mole. Then my second step is I decided to break down my chlorine. Breaking down a bond is through its bond dissociation energy, the amount of energy needed to break a bond. We know that Cl2 is chlorine and chlorine, so I have to break this bond and it takes that much energy, 243 kilojoules per mole. The reason that I have a half in front of it is because whatever I do to an equation, I have to do to the energy. Since I want 1 singular chlorine, not 2, that's why I didn't put a 2 in front of the chlorine to balance it. I put a half in front of Cl2. Therefore, I have to divide the energy by 2. Now I'm ready to make them ions. So my third step is, okay, take my sodium gas and ionize it with my ionization energy. Then after that, I take my 1 singular chlorine gas, add an electron to then make it a chlorine ion with the electron affinity. Then my last step is to take, there should be a sodium ion right here, typo, my sodium ion with my chlorine gas to make my sodium chloride. That gives you your lattice energy because the anion and the cation are coming together to form this crystal. That's the energy we don't know. So how do we solve for that? The Born-Haber cycle, just like in that image, but we're writing out the steps. So the heat of formation, right, the overall, which was, if I look back at my sheet here, which was negative 411, will equal all of my steps. Now my heat of formation was 108. My bond dissociation energy was 1/2 times 243. My ionization energy, 496. My electron affinity, negative 349. And I don't know my lattice. So you see that you have every single component and you can solve for your lattice energy. When you plug that in, your answer should be negative 788 kilojoules. And what you can do is you can plug this back in here and make sure that you get negative 411. Let's put that into your own practice. So use the following data to determine the lattice energy for calcium oxide. So let's see what has to happen. So calcium oxide is made from calcium. I know that calcium is a metal and exists as a solid, plus oxygen is a diatomic, so it exists as a gas, to make calcium oxide. All right, so what do I have to do? I have to make my calcium and oxygen into the ions. So my step 1 would be calcium solid to calcium gas, my sublimation. Then my second step would be, okay, doesn't really matter where you start, but if I just go in the order that I did before, O2 into 1O, right? Make my oxygen just 1. To balance, I put a half here. Then my next step, I'm going to ionize my calcium. Now here's the difference. Calcium can only undergo, well, not just calcium, anything can ionize 1 electron at a time. You can only lose 1 electron at a time. So this will lose an electron to become calcium plus with an electron. However, we want calcium 2 plus because we know oxygen has a 2 minus, so it has to ionize twice. So then that becomes calcium plus which will then lose another electron to become calcium 2 plus. Now let's look at the next step, oxygen. Well, my oxygen gas wants to gain an electron. That'll make it O minus. Since calcium is a 2 plus, I need oxygen to also be a 2 minus. So my O minus will then get another electron to become O2 minus. And then my last 7th step here, calcium 2 plus and oxide ion come together to form calcium oxide. Ooh, that's a little messy. So then let's see what that looks like. My energy here is 178. My bond dissociation energy is 498, so I would do 1/2 times 498. My ionization energy is the energy used to lose an electron. I'm given 2. Now, I didn't write here first or second. How do I figure out which one is the first ionization energy and which one is the second? Something I want you to notice is 590 is a lot less, almost half of 1,145. Now, when we talked about the trends of ionization energies, we know that the first electron is the easiest to lose. So this has to be the first ionization energy, and this is the second. So then I would take my 590 here and my 1145 here. Now we're here at the electron affinity. So again, I'm given 2 numbers. Now remember, electron affinity is not necessarily looking at a bigger or smaller number. We're looking at more negative. So it's the first more negative number is the easier one to gain an electron. Since this one is negative 141 and this one is a positive number, that's my first electron affinity. Because an atom can always gain that first electron a lot easier than the second one. So this is my second electron affinity. So I have negative 141 and 744. Now my heat of formation is my step that would go here, which would be 498 total. Oopsie, not 498. Negative 634.9. So let's write this all out. My heat of formation is equal to my heat of sublimation plus my heat of bond dissociation energy plus my heat of ionization energy 1 plus ionization energy 2 plus the electron affinity 1 plus electron affinity 2 plus my lattice. So then let's plug it all in here. We have negative 634.9 is equal to 178 plus 590 plus 1,145 plus negative 141 plus 744 plus the lattice, since we don't know that. I forgot one. Plus my bond dissociation energy. Doesn't really matter if you go in order. Awesome. So then if you calculate all that stuff together, what do you get? I'm going to give you a moment to plug it into your calculator. So remember, this was my heat of formation, my heat of sublimation, my bond dissociation energy, my ionization energy, my second ionization energy, electron affinity 2, and my lattice. And this is what I'm solving for. So then my lattice energy is equal to, if we plug everything in, 178 plus 590 plus 1,145 plus negative 141 plus 744 plus 498 divided by 2. So that's 2,765, and we want to move that over to the other side, so we subtract it. So then negative 634.9 minus 2,765 is negative 3,399.9. So then that is your answer for your lattice energy. So when you're getting different problems, you just always have to think this step. So sometimes you might be given already the ion, so you don't have to go through the sublimation and the bond dissociation energy. You just have to kind of think of what you're starting with and how you need to piece it together to get to your end result. Now there's 2 little trends when it comes to lattice energy. One is with the size of the ion. So if you look here at this picture, you should be able to notice that all my chlorines are the same, but then my ions are different. These are all my group 1 ions, and this is going down. I know that atomic size increases as I go down a group. So my sodium is larger than my lithium, my potassium is larger than my cesium. If you look at the distances between the atoms, they increase as the size increases. Because, right, if you all of a sudden have 2 bigger atoms, the size of them, but the particles from nucleus to nucleus, is just going to get bigger and bigger and bigger. So what this means with the lattice energy is as the distance between the ions get bigger, so as you go down the group, the lattice energy decreases. Remember, lattice energy is exothermic, so it has to be negative. So it decreases, meaning that it becomes less negative. That's what we look at. When we say lattice energy is increasing, we're saying it's becoming more exothermic, more negative. So if you look at the numbers here, lithium and chloride versus cesium chloride. Lithium chloride is negative 834. Cesium chloride is negative 657. This is less than this because it's more positive than this. So this one has our highest lattice energy. Because the distance is closer, so they feel the attraction between each other, forming that solid at a faster pace, therefore releasing more energy. Since these have a larger distance, for them to come together is going to take a lot longer, and they release less energy. Another trend is to look at the magnitude of the charge. So if we look at these 2 compounds, the lattice energy and then the picture to my right. So sodium fluoride. Sodium fluoride releases negative 910 kilojoules per mole. Calcium oxide. Calcium oxide releases negative 3,414 kilojoules per mole. That is a massive difference. Calcium and oxygen and sodium and fluoride. Now, if you look at the anatomical view, you could say, here on my picture to the right, sodium and fluoride have a distance of around 231 picometers. Calcium and oxygen have a distance of around 239 picometers. The distance is not very much because in size they're actually really similar. However, the lattice energies are really different. This is because of charge. Notice how sodium has a +1 and fluoride has a -1. So they're attracted to each other. But then calcium has a +2 and oxygen has a -2. They're attracted to each other even more because the magnitude of the charge is larger, therefore releasing even more energy. So the force of attraction between oppositely charged particles is directly proportional to the product of the charges. The larger the charge, they're just basically more attracted towards each other, and when they're more attracted towards each other, they release a higher amount of energy. With that said, let's practice those 2 things. The lattice energy of cesium fluoride is negative 744 kilojoules per mole, whereas that of barium oxide is negative 3,029 kilojoules per mole. Explain this difference. If you take a moment to look at your periodic table, figure out where cesium and fluoride are located and where barium and oxide are located. So cesium fluoride, cesium has a +1 charge, it's in group 1. Fluorine has a -1 charge. So their magnitude of charge is 1. Now, barium oxide. Barium is in group 2, it has a +2, and oxygen has a -2. So the magnitude is, if you multiply these together, that would be a -1, this would be -4. Way, way larger than this. The magnitude is a lot larger because the charge is larger. Therefore, it has a way bigger negative number. It's more exothermic. It releases more energy because barium oxide has more of a charge. Looking at the next one. Arrange these compounds in order of increasing magnitude of lattice energy. Potassium chloride, strontium oxide, rubidium bromide, and calcium oxide. Okay, so let's look at one at a time. Let's figure out which one is the strongest first. Calcium and oxygen, that's +2, -2. Rubidium and bromine, that's +1, -1. Strontium and oxide, +2, -2. And then calcium and chloride is +1, -1. So I'm going to make 2 little groups. since my charge magnitude of strontium and calcium is larger than potassium chloride and rubidium bromide, I know that my strontium oxide and my calcium oxide are on the larger side than my potassium chloride and rubidium bromide. So I know that. Now I want to pick it apart a little bit more. So now I'm just looking at my strontium oxide and my calcium oxide. How do I figure out which one is larger between the two? So strontium is lower on the periodic table in group 2 than calcium. Therefore, the distance here is larger than the distance between calcium and oxygen. Because strontium is further down the group, this is a larger atom than this. Therefore, it increases the size between strontium and oxygen, making it a lower energy and making calcium oxide the largest, more negative lattice energy. Awesome. So we know this is my first order. Now, what about potassium chloride and rubidium bromide? Now, rubidium is also a lot lower on the periodic table than potassium. Chloride and bromide are almost exactly the same, but rubidium and potassium have a pretty big difference. Rubidium is further down group 1 than potassium. So this one is larger. Therefore, the distance between rubidium and bromine is larger, which then lowers that energy. So therefore, my trend will be calcium oxide is my strongest, then strontium oxide, then potassium chloride, and then rubidium bromide. Looking at first, okay, what is my magnitude? Which one has a larger charge? Whichever has a larger charge is the most exothermic. Then you look at size. Those that are bigger, when you have a bigger atom, you're increasing the distance between the charges. If you're increasing the distance between the charges, it's going to take less energy, meaning it'll be a more positive lattice energy, and we always want more negative. So, since rubidium bromide is a larger distance than potassium chloride, it has the lowest energy.